In this video, I'm going to give you some basics about pointing a satellite dish. I recently had to move a dish from one satellite to another, and I figured it would be a perfect opportunity to pass that knowledge onto you. Many people think that pointing a satellite dish for broadcast is not hard, and in the grand scheme of things, it's not. But it does take a lot of patience and some specialized tools. I'm not covering the actual construction of a dish. That's just putting a pole up and assembling the dish, and once the dish is assembled, well, that is where the magic happens of pointing it in the right direction. Before we get our hands on the dish, let's cover some concepts. The satellites that we use for broadcast are in a geostationary orbit, 22,236,000 miles over the equator. This is where the satellites have to orbit in order to appear stationary to those of us on the ground. The satellites are assigned an orbital slot as referenced by a longitudinal location. The main commercial broadcast satellite is named SES-11 and is at 105 degrees west longitude. For me, here in Denver, that means that my dish will be pointing straight true south. While the satellite is in that orbital slot, it will typically move around a bit. The satellite operator will command the satellite to fire its thrusters to keep it within a box of about 22 miles wide. Here's a graph of some of the satellites that we track at my work, and you can see the hills and the valleys of the graph as the satellite traverses the box. This is why satellites have a lifespan and typically have to be changed out. Right now, as I record this video, the satellite SES-2 has reached the end of its life, not because the equipment on board is failing, but because the fuel required to keep it on station is running out. Right now, there are no ways to refuel satellites, so satellite operators have to calculate how much fuel will be needed to raise it to a graveyard orbit, which is 22,422 miles above the surface of the Earth. This is where satellites go to die, and it's kind of like a space version of Old Yeller. Have you ever had an audio issue that just made you upset? But don't worry, because one of the sponsors for today's video has you covered. Angry Audio offers all sorts of gadgets and gizmos. I want to focus on something specific, the Angry Audio Rave. It's their powerful yet affordable audio console built for radio stations just like yours. The Rave has 8 stereo line inputs, up to 4 microphone inputs, 2 output mix buses, 2 mix-minus outputs, a monitor feed for your control room, and so much more. The Rave is made of anodized aluminum, and it has avionics-style switches, silky smooth faders, and tally outputs for your on-air light. And the Rave isn't just for radio stations. It can also be used for podcasts. Get major market quality at small market prices. Learn more at angryaudio.com. Thank you, Angry Audio, for sponsoring this video. I've made this little model to provide visuals since I'm not that adept at After Effects to make models and illustrations. Besides, I can use this when training new people at work. So, here's our Earth with the satellites over the equator, and our little guy is pointing a satellite dish. I didn't have anything to make a satellite dish, but he's still standing there pretending like he's pointing a satellite dish. So, azimuth is our left-right pointing motion. So as we go across, that's left, that's our azimuth. That translates to east-west. Taking SES 11 as our example, if you were in New York, let's say over here, you would be pointing southwest. If you were in Los Angeles, you would be pointing southeast. Next is elevation. This is the up and down motion of the dish. The farther you are away from the longitude that the satellite is parked over, the lower in the sky that the satellite will be. Looking straight south will be the highest angle that your satellite dish would look. So looking again, if we're right here, if I were to move this just straight across, we're now shooting over SES2, this one. Really come back across. Here we go. Finally, you have polarization. This is one of the key parts that people forget about. Generally, broadcast signals on a satellite are either horizontally or vertically polarized. This means that your LNB will look at signals only coming from one direction of polarization. The opposite polarization will be ignored or filtered out. This allows satellite operators to maximize the amount of paying customers on the satellite. If your polarization is correct, you won't receive any interference or signals from the opposite polarity. So, as your look angle is farther east or west from you, you'll need to skew your polarization a certain amount in order to be vertical or horizontal to the satellite's orientation. Looking again at our model, if you are at SES2, you're doing horizontal, because that's how I can get my hand over here. You're looking at it like this. Can you see that? Here, let's do it like this. Aha. So, from our little guy's perspective over here, he is looking at it like this. This is horizontal. But if he were to move his dish over to SES 11, well, now we're kind of, off of what SES 11's version of horizontal is. So we'll need to twist our LNB, rotate the polarization of it, so that way we're horizontal with the new satellite. In my day job, I have many stations tell me that their X service is working fine on the same satellite, or that they have Y service that has a higher EBNO than ours. That basically tells me that their polarization on their dish is not correct. Some satellite customers don't have any traffic on the opposite polarity to interfere with the signal that they're trying to get when their LNB is off its polarity. So as we rotate off of the correct polarity, vertical in this example, we see that the intended signal, or copole, coming down, and the cross pole, the opposite polarity signal, come up. Polarity is just as crucial as azimuth and elevation, so don't skip it. There are a lot of satellites in geostationary orbit. Here in Denver, I can see over 250 geostationary satellites across the sky. So getting yourself in the ballpark before you start swinging the dish is going to save you a whole lot of time. And this is where the first tool that you need is going to come into play, and it's free. Before you go outside, jump on your computer, go to dishpointer.com. And it's nice because it gives you this line to show you the path, so you can have some points of reference to get your dish in the right place. So when you put it on there, you see your pin, and then there's a line that points towards where the satellite is. It's great because you can actually see what you're looking for. It'll also give you your compass directions so you can point the dish. There is also an app called Dish Pointer Pro. This is what I've used every time I've had to point a satellite dish. I have Dish Pointer up. So, as I kind of move it across the sky, I kind of get an idea of where we are. So, 87 degrees, which is SES2, is basically over that tree right there. And then we are gonna bump it over to 105, which is basically this tree right here. So, and I've got the sun right in the way. Who thought it was a good idea to film at this time of day? That would be me. Just remember that for a magnetic compass, you should be about 3 feet away from objects to ensure that there is nothing interfering with that compass. Hi, I'm going to take a moment here and recognize the sponsor of today's video, LinkUp Communications. When your content has to get to your audience, you can count on their content distribution using XDS and other industry-leading platforms. LinkUp has provided distribution solutions with the highest degree of reliability for over 3 decades. If you're wanting more information about their services or just who are they, visit their website at linkupcommunications.com. And now, back to the video. Okay, we have our prep done, it's out of the way, and now it's time to actually point the dish. So, let's gather our next set of tools. You're obviously going to need some big wrenches, and these will be determined by what kind of hardware you have on your dish. But what will be helpful for all dishes will be a satellite finder like this XR3, make sure it's up to date, and a spectrum analyzer. It could be any spectrum analyzer. You connect the spectrum analyzer to the indoor port of the XR3, and the outdoor port gets connected to the LNB on the dish. The XR3 will power the LNB while feeding the signal to the spectrum analyzer. While you can point it with just an XR3, having a spectrum analyzer makes the process so much easier. Trust me, I've been there. It is so much easier with the spectrum analyzer. First, you need to loosen up the bolts that hold the dish in position. Just loosen the ones that you need to move the dish, and only enough to allow you motion. You don't want the dish to fall apart on you. Then, this time lapse I'm about to show you, while it's about 10-15 seconds, it was about 30 minutes of real time, and the whole process itself took about a couple of hours. So you kind of have an idea of how much time you need to budget for pointing a dish. And as you can see, I'm starting with the azimuth and adjusting that. It's small motions at a time. A quarter turn of the nut that pushes the dish. Then I'll move on to the nut that adjusts the elevation. Finally, I'm rotating the feet of the dish to ensure that my signal is peaked on the polarization that I'm looking for. Notice that I do go back and forth. Something to watch out for is side lobe. This is a spot off of the main signal that appears to be a signal, but it really isn't. To illustrate this, I have a flashlight shining against my back wall. Notice that there's this main signal, that's the main flashlight beam, and all around it, in this little area here, is a secondary beam, if you will. That is basically the side lobe. It's not as bright as the main beam. But if you were to aim your satellite dish at that point on the side lobe, you would have low signal and maybe even no signal if you were at the edge of the box. If the satellite moved, or as the satellite moves through the box, your dish would eventually be pointed at open space. So, see how this area is all, it looks like there's signal there, but it's kind of like a fake signal. You want to be pointed at as close to the center of this main beam as possible. This is why you need to go through the signal. You'll start to see the signal come up and peak, continue going until you get back to the lowest signal, then go back and find the peak again. And you basically go through it in smaller and smaller and smaller movements until you get to the peak. And this goes for all 3 movements of the dish. Once you're peaked, tighten the bolts down, check your signal again, because as you tighten things up, you may find that you come off of the peak. So pay attention to how tightening the bolts moves your dish. Then compensate for that when you peak the dish. You may have to do that a couple of times. And that is pointing your satellite dish. Okay, to recap, you're moving your dish on 3 directions: azimuth, elevation, and polarization. You're going through the peak to make sure you're not on a side lobe, then coming back to the peak. And everything is small motions, small motions. Using the correct tools will help you make this a relatively painless process. Just be sure to allocate plenty of time and have a lot of patience. Thanks for watching. Until next time, stay safe, stay healthy, and keep learning.